In this video we are going to look at some application problems and how to apply different forms of exponential functions to those problems in order to solve. So this first one, we're going to assume that we have a half-life of 5,728 years. And we want to know how long it would take for 3 grams of carbon-14 to decay down to 1 gram. So the first thing we have to do is kind of write down a few things that we know. So we know that we are starting with 3 grams of carbon-14. We also know that we want to end with 1 gram of carbon-14. Beyond that, we know that the equation we want to use for my half-life of carbon-14 is A naught e to the negative 0.123121 t. Okay, so this is the equation that we want to use. This equation is kind of like a standard given equation. It doesn't change, but it is very specific. This is specific just to the half-life of carbon-14 decay, or looking at carbon-14 decay. So here we have to be able to solve things down. So we need to input or plug in. So I know what A of t is going to be. It's 1 gram. So this is going to say that 1 is equal to, my initial was 3 e to the negative 0.000121 t. And now my goal here is to solve and get t by itself. So the first thing I'm going to do is divide everything by 3. So I have that 1/3 is equal to e to the negative 0.000121 t. Now the next thing that I want to do is I'm going to get rid of this e. And the way that you do that is by raising it to the natural log. So I'm going to take the natural log of my 1/3 is going to equal the natural log of e to the negative 0.000121 t. When we do that, we're left with the natural log of 1/3 equals negative 0.000121 t. The last thing we need to do is get t by itself. So here we're going to have the natural log of 1/3 divided by negative 0.000121, and this gives me my t value. When you evaluate that, you end up with 9,079.44 years equals your t. Okay? Let's take a look at this next one. Suppose we have a population of bacteria in a petri dish that has a doubling time of 1.5 hours. How long will it take for an initial population of 10,000 to reach 100,000? So first of all, we have to look at the equation that we're going to use. So we have P of t, notice it's a capital T, is going to equal my initial A to the t over big T. Okay, so that's going to be essentially some of the idea in terms of our doubling time. Now, what do we know? We know that the time it takes to double is 1.5 hours. So big T is the time it takes to double. And this was 1.5 hours. We also know that my A is going to be doubling time. So doubling time essentially means 2. We also know that we have an initial of 10,000. Sorry, 1 too many zeros. And we know that we have a final count that we want to be 100,000. So now that we have all of our information, we can actually start plugging in what we have to solve for what's missing. So this is the equation that we're using here. So we're going to have 100,000 bacteria is equal to my 10,000 bacteria times 2 to the t over 1.5. So we have plugged everything in, and now we have to work on solving. So the first thing I'm going to do is divide everything by 10,000 to get that out of there. So this is going to leave us with 10 equals 2 to the t over 1.5. Now with this, one of the things I can do is I can raise both sides to my log. So I can say the log of 10 is equal to the log of 2 to the t over 1.5. A few things are going to happen. First, this right here will now follow the power rule. Second, this part over here, this is going to undo each other. And the reason for that is because there is no base written, which means we can automatically assume it's the base 10. So here when we solve, this means we have 1 equals. The power rule says this becomes t over 1.5 log of 2. I need to get t by itself. So I'm going to multiply everything by 1.5. So this is going to give me 1.5 equals t log of 2. So I'm going to divide. I have 1.5 over the log of 2. It's going to give me my t value. So in this case, we are going to have that 4.98 hours is my t. And that's all there is to that one. Alright, let's look at this last and final one. So here, Wayne has $12,500 in a high interest savings account at 3.66% annual interest, compounded monthly. Assuming he makes no deposits or withdrawals, how long will it take for his investment to grow to $15,000? So first of all, we are going to use A equals P times 1 plus R over N to the NT. Just like before, we need to look at what it is that we have. So we know that P is going to be 12,500. We know your rate is going to be 0.0366. Do not round. We know that your amount is going to be $15,000. We also know that you are compounding monthly, which equals 12. So it's 12 times that year you'll compound. So we need to plug everything in that we have. So here this is going to be 15,000 is equal to 12,500 times 1 plus 0.0366 over 12 raised to the 12t. So I have to start solving this down. So the first thing I'm going to do is divide everything by 12,500. So this becomes 1.2 is equal to 1 plus 0.0366 over 12 to the 12t. Here I'm going to take the log of both sides. So the log of 1.2 is equal to the log of 1 plus 0.0366 all over 12 to the 12t. We then have this piece right here, which is the power rule. And so here I'm going to leave the log of 1.2 alone for the minute. So this is still the log of 1.2 is equal to 12t log of the stuff. And if we were to do out the stuff, you should come up with something close to 1.00305. We need to get we need to get t by itself. So in this case, we're going to divide everything. So this becomes the log of 1.2 divided by 12 log of 1.00305 gives me my t value. In this case, we're going to end up with 4.99 years is my t value. So there you have it. Everything that you kind of need to get started with and work with solving applications as they relate to logarithmic and exponential ideas. So if you have any questions, please let me know. If you find an application that you are just totally stumped with, feel free to send that to me. I'd be more than happy to take a look. Otherwise, I do hope you enjoyed this video as much as I did, and I'll see you next time.